In this video, I'm going to demonstrate how we can generate equations of motion using the torque-angular momentum relationship that we just introduced. And we're going to use the pendulum example that we did last week. So just to write out what that is, we have a particle P that has a mass, and it is connected to this rigid rod here, which has a length of L. 2.0, and then it can rotate about 0.0, and so this is fixed. And we draw our reference frames in the following way, or I'm drawing them in the following way here. We have, this is our fixed frame A, and then here we have our fixed frame B, but that's B2. And this is B1, and then that allows us to define theta here, and that's in the positive direction. So that means the angular velocity of frame B in frame A is going to equal a positive theta dot B3. So just like last week, we first start off by defining the number of degrees of freedom of our system, and that is 1 in this case. And then we also define the coordinates, or coordinate in this case, which is theta. And this again tells us the number of degrees of freedom tells us the number of equations of motion we need, and the coordinates tell us what variables or coordinates this equation of motion should be in. What are the unknowns? And that is, in this case, theta and its derivatives. And then our next step is to draw our free body diagram or diagrams. Here we only need one. So we have our particle P, and we have two forces acting upon it. We have gravitational force, mg, plus we have a tension force acting through the rod, so T. Next, let's just write out what our angular momentum and torque relationship is for reference, because essentially now we're just going to fill in what these terms are. So we have the torque about a point P, and here we're going to write that about point O. Right, so this origin point here. And so the torque of point P about O is equal to the derivative of our angular momentum of P about O plus the velocity of point O in frame A cross with the linear momentum of point P in frame A. And so we'll start with this torque term here. So here we have torque about point P about point O. So if you recall from the last video, our torque is equal to a position vector ROP, crossed with our force vector. So we can write out what those two vectors are here. So we have ROP is equal to L in the B1 direction, and our force vector is equal to mg in the A1 direction minus T in the B1 direction. So that allows us to write torque as the cross product between LB1 and mgA1 minus tB1. So just like regular multiplication, we can distribute out these terms here. So we get torque is equal to LB1 crossed with mgA1 plus LB1 crossed with negative TB1. And the first thing you should notice is that we have two cross product between two B1 terms. And these two terms are unit vectors are parallel to one another. And so what that means is that this here is going to go to 0. So we can get rid of that term there. Now, what we're left with is the cross product between LB1 and MGA1. And now you should notice that our unit vectors are in terms of different frames. And so that means that we have to convert one of these terms such that both are in the same frame. So we're going to take this B1 term and we're going to write that in frame A. So you should again remember that we have the relationships between our two unit vectors. So B1 and B2, we can write that as we have cosine theta, sine theta, negative sine theta, cosine theta. And this is A1 and A2. And so with this relationship in mind, we can now write B1 in terms of A1 and A2. So we have the following. We have torque, and the other thing is we can kind of lump these three other terms, so the MGL terms, and so now we have our B1, so that's cosine theta A1 plus sine theta A2 crossed with A1. And again, we can distribute it out. You should also notice that when we take the cross product of this term here, which has an A1 in it, and our A1 unit vector, that this will go to 0. So what that means, again, is that all we have to worry about is MGL sine theta A2 crossed with A1. And A2 crossed with A1 is going to give us a negative A3. So we now write this as torque is equal to MGL sine theta A3. And I should be careful, these are all P about O, P about O. Okay, so here we have this, we've found this first term here. And so the next thing we're going to do is actually calculate this derivative of angular momentum. So to do that, I'm just going to quickly clear the screen so we have a little bit more space. Okay, so now that we have torque, we need to go and get the next term, which is right here. So we're going to get the derivative of angular momentum. So first we start by just getting angular momentum, which you should recall from the last video as the following. We have ROP crossed with linear momentum. So sorry, that's a P there. And we can rewrite that as ROP crossed with M times the velocity. So ROP is equal to LB1, and so to get the velocity, we get the derivative of that. So we have the derivative of LB1 in frame A, which is using the Magic formula, equal to LB1 plus, and then here we have a positive theta dot times B3. Again, this is theta is positive, which is why we wrote that here. And so that's crossed with our position vector, LB1. So this term actually ends up going to 0. And so what we're left with is L theta dot, and then we have B3 crossed with B1, which is equal to B2. So now we can plug these terms in order to get our angular momentum. So we have, again, our position vector LV1, and that's crossed with m times our velocity vector, so L theta dot B2. So we can write that as, take all the terms out, so we have m L squared theta dot, and then what we're left with is B1 crossed with B2, and that gives us B3. Now, we need to take the derivative of this. So we can do two things. One is we can take this derivative and we can use the magic formula. The other option is that you can recall that A3 is equal to B3, right? This was introduced back a few weeks back. So you can use this relationship and you can rewrite angular momentum as being ml squared theta dot A3. So to take the derivative in frame A, simply going to equal ml squared theta double dot A3. So either way, if you took the magic formula, you'd get this answer in terms of B3, or again, you can use this relationship here. So now we have this term here. And so we only have one more term to calculate, and actually don't even need to clear the screen for this. I'll just write it out here. And we have the velocity of point O in frame A crossed with the linear momentum of point P in frame A. And think of what the velocity of point O is in frame A. Well, O is the origin of A, so that means O doesn't move. It's fixed in frame A. So what you'll get is 0 crossed with linear momentum. And that is just going to equal 0. So this is an example of where, again, this term, while important to remember, in this case it does actually go to 0. So if we have our, right, so here we have, I'm just writing our other term, so HPO is equal to ml squared theta double dot A3. So now we can simply just plug these two terms into our equation. So let's do that and get the following. Okay, now that we've again cleared some space, let's plug in these terms. So we have torque is equal to mgl sine theta A3, and that is equal to our derivative of angular momentum. So that's ml squared theta double dot A3. And then this term went to 0, so we don't even have to worry about it. So this was our equation of motion. We just need to simplify. So we can get rid of A3 on both sides, the m on both sides, and an L term. And so that leaves us with negative g sine theta equal to L theta double dot. And so we can just simply rearrange that to be L theta double dot g sine theta equals 0. So this here is our equation of motion. And you should notice that it's exactly the same as the equation of motion we arrived at when we calculated it using the force linear momentum relationship. So in the next video, I'm just going to show another example, yet again, of how we can use the angular momentum torque relationship in order to generate equations of motion.